Hello and welcome to this revision session for AQA A-Level Physics. In this revision session we'll be looking at astrophysics. So in this revision session we're going to look at answering examination questions for AQA A-Level Physics option astrophysics. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for AQA A-Level Physics. So how do you carry out this revision session? So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out, whilst on the right hand side write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So how can you revise for AQA A-Level Physics and the astrophysics option? So firstly, learn the key facts. Use the revision guides, workbooks, prep notes and textbook to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself. Second step is to test yourself. Use Caboodle, Seneca, student knowledge checkers to test your own understanding, and you may wish to do this from your own cue cards. Then finally, practice examination style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer exam style questions and mark your own work, and you may wish to download your own examination past papers to do this. So learning the key facts, then testing yourself and practicing exam style questions is how you should revise AQA A-Level Physics. So let's have a look at some questions for astrophysics based on the 2022 Advanced Examination information. So the first question says, the summit triangle consists of three stars, Altair, Deneb and Vega. Some of the properties of the three stars are summarised in table 2. Firstly, deduce which of the three stars appears the brightest, and then calculate the distance from the Earth to the closest of the three stars. So pause the video now, then unpause the video when you want to go through your answer. Right, in this particular question you've got to understand how apparent magnitude, which is given in the table, links to brightness. Now you've got to be aware that the lowest value of apparent magnitude indicates the brightest star. The lower the apparent magnitude, the brighter the star appears in the Earth's sky. So from looking at this information, Vega has the lowest apparent magnitude, so therefore will appear brightest in the Earth's atmosphere. Now the next question says calculate the distance from the Earth to the closest of the three stars. Now again, what you're going to have to do is use our equation, apparent magnitude minus absolute magnitude equals 5 log d over 10, where d is going to be in parsecs. So to work out your value, you would find your difference in apparent magnitude and absolute magnitude. You can then pop it into the equation to work out d. Now you can do this for all three of the stars and then work out which is the closest. So this one is Altair, so therefore you can see that Altair is going to give you an answer of 5.2 parsecs. Now as well as that, you can also work out that Altair is going to be the closest of the three stars because the difference between its apparent magnitude and its absolute magnitude. So you can see that it appears it appears bright in the night sky because it's got an apparent magnitude 0.77, but its absolute magnitude, its actual brightness, is going to be quite a bit dimmer. So therefore it indicates it's going to be the closest. So that's a quick way of working out which is going to actually be the closest of the three stars. So you can work it through like that. The next question says, draw a ray diagram for an astronomical refracting telescope in normal adjustment. Your diagram should show the path of 3 non-axial rays through both lenses. Label the principal foci of the two lenses. So pause the video now, then unpause the video when you want to go through your answer. Right, so when you're answering this particular question, you've got to be able to draw a ray diagram for a refracting telescope in normal adjustment. Now remember, normal adjustment means that the two lenses in your refracting telescope share the same focal plane. So when you're drawing it, you should indicate that the principal axis is drawn and then the principal foci of both of the lenses coincide with each other and are on this principal axis. That's the indication of normal adjustment. And then to show you 3 non-axial rays drawn correctly. So what you'll have is non-axial will mean that they will not be parallel to the principal axis. They'll be at an angle, and they will then remember to draw it through, so it goes through your first lens and then your second lens to then draw your image in like so. The next question says, most modern optical observations make use of reflecting telescopes rather than refracting telescopes. Discuss the principal optical advantage of reflecting telescopes. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you are able to describe the advantages and disadvantages of reflecting telescopes and refracting telescopes. So let's just have a look at the two of them. So the first thing to understand is as follows, that your reflecting telescopes will not suffer from chromatic aberration. So chromatic aberration occurs when light of with different wavelengths refracts through a lens, and because the different wavelengths or colours will have different different lengths to which they will focus their image to, because of the wavelength linking like that. So that means that your red, your blue, your green will all come out at different points, because they'll all have a slightly different focal length from that lens. So as a result, you get that chromatic aberration. Now, because there's no refraction going on in your reflecting telescope, that indicates that this will not take place. So reflecting telescopes do not have chromatic aberration. The next thing to note is you can easily make reflecting telescopes larger. Now, this has two major advantages. So because you can make reflecting telescopes larger, because it's easier to support them, because you can actually have a support behind the actual telescope, because the radiation doesn't need to go through the telescope. You can place a support behind it. Because they can be built larger, it gives you two important things. The larger area means that you get a greater collecting power, and also having the larger area for your mirror will give you a smaller minimum angular resolution. So as a result, you can see things in more detail. Now, in addition, when you got parabolic mirrors, you won't get spherical aberration, which is another advantage of reflecting telescopes. The next question says, the Greek astronomer Hipparchus used naked eye observations to develop a scale for comparing the apparent magnitude of stars. Firstly, explain what is meant by apparent magnitude and describe the main features of the Hipparchus scale. Right, so pause the video now, then unpause the video when you want to go through your answer. Right, so it's very important you can describe the Hipparchus scale and link it into apparent magnitude. So what should we be aware of? Right, firstly, apparent magnitude is based on how bright a star appears on the Earth. So remember that definition. Apparent magnitude is how bright a star is from the Earth, from that position of us. Now, it does depend on two things. Firstly, the absolute magnitude, which is how bright the star actually is and how far away it is from the Earth. Now, larger values of apparent magnitude are given to dimmer stars, and lower values of apparent magnitude are given to brighter stars. Now, originally, when Hipparchus came up with this scale, he assumed that the brightest stars had a value of 1, and the dimmest stars he could observe with his naked eye had an apparent magnitude of 6. Now, we also then said it was a logarithmic scale, where magnitude 1 stars are 100 times brighter than magnitude 6 stars. So therefore, that tells us, as we're working on a logarithmic scale, that at a difference of 1 on the apparent magnitude scale is a difference in brightness of a factor of about 2.51. So to work out the difference between 1 on the scale and 2 on the scale is just 2.51 to the power of 1, whilst a difference between 1 and 3 on the apparent magnitude scale will give you 2.51 to the power of 2, so 2.51 squared, to tell you the difference in brightness. Now, applying the apparent magnitude of the Hipparchus scale give us some issues with this, because Hipparchus didn't realise that, for example, the sun was a star, so therefore that was brighter than the brightest value he gave on his scale, which was 1. So therefore we have to give very, very bright stars negative apparent magnitudes. Now, when you're giving your answers, please make sure you give your answers in a coherent structure with a style, and you got your information set out coherently. So you got to have a clear description of what's meant by apparent magnitude, what's the definition, the idea that it's a logarithmic scale going from 1, which is the brightest, and 6, which is the dimmest, understanding how Hipparchus determined this, and then also possibly discussing some errors that were in the scale. So for example, he didn't realise that the sun was a star, so we now have to give negative values to very bright stars such as the sun, and also you could only see up to apparent magnitude 6 with his eyes, so therefore now we can now see dimmer objects with our telescopes. We've got to give them values larger than 6. The next question says, in 2013, a gamma-ray burst was detected from a region of space between the constellations of Leo and Ursa Major. State the event that was the likely cause of this gamma-ray burst. Then measurements of the optical remnant of the event revealed an object with a redshift of 0.34. Calculate the distance to this object in light years, give your answers to the appropriate number of significant figures. Then the total energy of the gamma ray burst was estimated to be 10 to the 47 joules. Many scientists are concerned that a gamma ray burst in the direction of the Earth could cause major problems. Show that this is the similar to the energy that will be released if the mass of the Sun was all converted to energy. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first one is you've got to be aware of what are the common causes of gamma ray bursts, GRBs, in astrophysics. Well, they tend to come from the collapse of a supermassive star into a neutron star, or the collapse of a supermassive star into a black hole. Those events that lowering in the value of absolute magnitude will allow that release of gamma rays to be happening in this GRB. Now, the next one, it's a bit of a more challenging question because you're going to have to use two equations. Now we know that from the equation sheet that Z is equal to V over C. So we can rearrange this and make V our subject. So we can say V is equal to Z times by C, C being the speed of light, 3 times 10 to the 8. So we say 0.34 times by 3 times 10 to the 8 gives us a value of 1 times 10 to the 8 meters per second. We can then use our Hubble's law equation, V is equal to Hubble's constant times by D, so V equals HD, to then work out what our value of D is, because that's what the question is asking you. Work out the distance in light years. So we can say that D is equal to V over H. Now, it's important on two things here. With our value of Hubble's constant, which is going to be 65, we've got to be aware that we have to use our velocity in the units of kilometers per second. So whilst our previous question worked out the value of our velocity to be in meters per second, in this particular question we need to use kilometers per second. So as a result, we have to convert 1 times 10 to the 8 meters per second into 1 times 10 to the 5 kilometers per second. So we pop that in and we get an answer out to be about 1,600 megaparsecs, because if you think about the units of the Hubble's constant, that is what we get our distance values out as. So we can therefore say that we've got our distance now in megaparsecs, but then we need to convert this into light years because that is what the question wants. Now, the conversion from megaparsecs into light years can be done into two different sections. So firstly, convert megaparsecs into parsecs, so you times your value of 1,600 megaparsecs by 10 to the 6 to go from megaparsecs to parsecs, and then multiply by 3.26, because the conversion from parsecs into light years is that there are 3.26 light years in every parsec, so you get our answer to be 5.1 times 10 to the 9 light years. Now, it's important to note that we give our answer to two significant figures because all the values given in the question are given to two significant figures. Now, in the last question, we're working out the energy released if the mass of the Sun was all converted to energy. So you do E equals mc squared, our equation that links energy and mass. So we say E equals mc squared, C is 3 times 10 to the 8, m is the mass of the Sun, which is 2 times 10 to the 30, a value which is given to you on your equation sheet. So we get 2 times 10 to the 47, which is on the order of magnitude of 10 to the 47, so it is proven to be the case. The next question says, define the parsec and use a diagram as part of your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, what is a parsec? So by definition, a parsec is the distance at which 1 AU, okay, so 1 astronomical unit, the distance between the Earth and the Sun on average, subtends an angle of 1 arc second, or 1/3600th of a degree. Okay, and you can use this by drawing a diagram in there, so we can draw this in to show this particular this subtending of an angle occurring when you have a distance of 1 AU between the position of the planet which observes the star on. The next question says, Table 2 summarises some of the properties of 4 stars in the constellation. Determine the absolute magnitude of Sarin. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, we've once again got to use our equation a paramagnitude minus absolute magnitude equals 5 times by log d over 10, where d is given in parsecs. So we can say we want to work out big M, so we can say small m minus big M equals 5 log d over 10. We've got small m from the table. We know what the distance is d from the table, so we pop our values in, rearrange it, make m the subject, and we get our answer to be 1.3. So our absolute magnitude is 1.3. The next question says, describe the links between galaxies, black holes and quasars, and at a distance of 5.81 times 10 to the 8 light years, Markarian 231 is the closest known quasar to the Earth. The redshift of Markarian 231 is 0.0415. Use these data to estimate an age in seconds of the universe. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you can tell the difference between galaxies, black holes and quasars. Now you've got to remember that quasars are things produced by supermassive black holes. So what a quasar is a black hole at the centre of an active galaxy, an AGN, an active galactic nuclei or nucleus. So what happens is that when material falls into a quasar as is accelerated towards this particular black hole in the quasar, it will then emit radiation, okay, which is what the quasar is, and that radiation has been redshifted as it's travelled through the universe to be in the radio spectrum. So the quasar is a bright radio source due to the emission of radiation as matter goes into a supermassive black hole in the centre of an active galaxy. Now this next question, once again, like the previous question, we're going to have to link our two equations. Now we firstly know that Z is equal to V over C, so therefore V is equal to C times by Z. So we know C is 3 times 10 to the 8. We're given Z in the question, so we get our answer in meters per second. Again, now we're going to use the idea that we want to use V equals HD and then H equals V over D. But a couple of things on this. Like mentioned before, for our equation, V is equal to HD. V needs to be in kilometers per second, so we've converted 1.25 times 10 to the 7 meters per second into 1.25 times 10 to the 4 kilometers per second. Now we need to have a value for D. Now because Hubble's constant uses the distance value to be in megaparsecs, we've got to convert our value of light years, which is 5.81 times 10 to the 8 light years, into parsecs. How do you do that? You divide it by 3.26 to get 1.78 times 10 to the 8 parsecs, and then we then divide that by times 10 to the 6 to get that into megaparsecs, which is 1.78 times 10 to the 2 megaparsecs. Because remember, for Hubble's constant to be used in its correct format, velocity has to be in kilometers per second and distance has to be in megaparsecs. So we therefore do our velocity in kilometers per second, 1.25 times 10 to the 4, divided by distance in megaparsecs, 1.78 times 10 to the 2, to get our value to be about 70 kilometers per second per megaparsec. Now the age of the universe is 1 over h, so therefore what we can therefore do is do 1 over h and work it through like that. But then we've got, if we're going to do it via that methodology, we're going to have to convert values into the correct formats. So in this point, to work out the age of the universe, which is 1 over Hubble's constant, so therefore is distance over velocity. Distance has to be in meters, so we'll convert our light years into meters by again using a conversion factor, which is 9.47 times 10 to the 15. So we therefore do 5.81 times 10 to the 8 light years times by 9.47 times 10 to the 15 to get it into meters. We then divide it by meters per second, which is 1.25 times 10 to the 7, to get our answer out for time in seconds, which is 4.42 times 10 to the 17 seconds. The next question says, a typical quasar is believed to be approximately the size of the solar system, with a power output similar to that of 1,000 galaxies. Estimate with reference to the inverse square law how much further the most distant visible quasar is likely to be compared to the most distant visible galaxy. So pause the video now, then unpause the video when you want to go through your answer. Right, with this type of question, you've got to use the inverse square law and you're going to have to equate them to each other. So we're going to say that the quasar and the galaxy are going to have the same brightness. So we'll therefore have the same received power. So we can therefore say for our inverse square law that power of the object divided by distance to the object squared is going to be a constant. So we can say the power of the quasar divided by the distance to the quasar squared is equal to the power of the galaxy divided to the distance to the galaxy squared. Now we already can say that if we say the power of if we can say that the power is going to be, of a galaxy is going to be 1, well then the power of a quasar is going to be 1,000. So there, because we're just ratioing the two, because we say that a galaxy has 1,000 times more power output than one galaxy, given in that first sentence of the question. Now if we then just state our distance to the galaxy to be 1, we can find out how much further away that particular quasar could be. So we do 1,000 of the power of the quasar divided by distance to the quasar squared is equal to the power of the galaxy, which is equal to 1, divided by the distance to the galaxy, which is 1. We can work it all the way through, and we can then work out that the distance of the quasar is going to be 1,000 to the power of a half, so the square root of 1,000. So therefore we get that it can be about 30 times further away than the galaxy can be. The next question says, evidence to support the Big Bang theory comes from the cosmological microwave background and the relative abundance of hydrogen to helium in the universe. Explain what is meant by the cosmological microwave background radiation and how its existence supports the Big Bang theory. So pause the video now, then unpause the video when you want to go through your answer. Right, in this particular answer, you've got to understand what the CMBR is and why it's so important to the Big Bang theory. So the CMBR is the radiation coming from all parts of the universe. It is in all directions, okay, it's in the background. So what happened is that when the universe cooled after the Big Bang, when it cooled enough for matter and radiation to decouple from each other and from radiation to spread through the universe, okay, which occurred when protons and electrons first combined to form atoms, well, this radiation was released into the universe. Since that point, the universe has expanded and expanded and expanded. This means that this radiation has stretched with the expansion of the universe and has redshifted into the microwave spectrum. Now it's important to note that this spectrum is in the microwave region, so its peak of its black body radiation wavelength is it links to a temperature of about 2.7 Kelvin. Now this is the radiation left over from the Big Bang. It is the photons released when the first atoms formed in the universe and allowed radiation to stream through the universe, which could only have happened if there was a Big Bang. The next question says, explain how the relative abundance of hydrogen and helium supports the Big Bang theory. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, it's important you've got to understand how the amounts of hydrogen and helium, whether 75% hydrogen and 25% helium, supports the Big Bang theory. Now, the Big Bang theory suggests that the universe was created in a very infinitely hot, very short second, and resulted in a very small universe, a very hot universe. Since that point, the universe has expanded and cooled since then. Now, it's important to note that at the start of the universe had a high enough temperature to cause hydrogen to fuse into helium. So when the first hydrogen atoms were formed, they could then fuse into helium in that high temperature situation. But that fusion would stop when the universe cooled and cooled because the universe was expanding. Now this allowed us to have an abundance of 25% helium and 75% hydrogen, a 3-to-1 ratio, because of the time it took for the universe to cool. So the idea is that because the universe cooled down in a certain time period after the Big Bang, it only had enough time for 25% of the hydrogen to fuse into helium, and since that point the conditions have never been hot enough for fusion to occur, leaving us to our ratio of 3-to-1 hydrogen to helium. So I hope you've enjoyed this particular revision session. If you've been successful and learnt in today's revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for AQA A-level physics. So thank you very much for watching this astrophysics revision session for AQA A-level physics on the 2022 examination series. Thank you very much and have a lovely day.